Welcome everyone to this video. Um, so this is like a one-off video in which we'll be discussing one question uh, from the book Irodov. So the question is from the chapter of atomic and nuclear physics. It's question number 5, I think. So let's begin. Basically, it's kind of an interesting question, which the kind of which I have not seen before, actually. So I want to discuss a little bit about it, and you will also learn something new from it. So one of the things which we learn first in nuclear physics, atomic and nuclear physics, is that there is something called nucleus in an atom. So electrons they revolve around the nucleus, and it was discovered by Rutherford and his basically students, um, or you can say his associates, when they were conducting the gold leaf experiment, or the basically experiment in which they had like a gold leaf on which they bombarded the alpha particles, or we can say the alpha particle scattering. So basically, they were able to establish that there is some kind of very heavy uh, particle situated inside an atom. So basically, that particle it has all the positive charge of the whole atom, and when some kind of other positive particles try to approach that, uh, uh, basically what we say subatomic particle, then it gets deflected. If it is coming towards the nucleus or whatever particle they had named at that time, uh, in such a way that it is going to get head-on collision, uh, then it will get simply reflected back. If it is approaching at some particular distance, like this is the nucleus, let's say, and Z is the what we say atomic number, and E is the electronic charge. So this is the nucleus which we have. So we have discussed in Rutherford model of atom that electrons revolve this nucleus. And basically, in the alpha particle experiment, alpha particles are projected on this nucleus and they get deflected. So let's say an alpha particle is coming like this, okay, and it gets deflected like this, right? So on the basis of these deflections, they were able to establish that okay, the alpha particles they take different paths. A particle is approaching uh, uh, in its line of collision, then it will definitely get reflected back. Or basically, when it is approaching in such a way that okay, it's going to collide head on with the gold nucleus, then it will get reflected back. So basically, what is the angle with which the alpha particles get deflected? So in case of alpha particles, in place of alpha particles, let's take protons. So we have a proton here. This proton, it gets deflected from this positively charged nucleus. So the question which we have in uh, the text which we are referring to is that okay, what is the momentum imparted to the proton by the Coulomb field of this gold nucleus? So what do you think? How will we approach this problem? Let's say we have the distance, we have this distance called b. This is called the aiming parameter. So this aiming parameter shows the distance between line of approach of the incoming particle with the stationary gold nucleus. We have to use the word stationary because that we'll be assuming it is not moving at all, which is not true practically. If we are talking about some interatomic particles, interatomic distances within the gold foil, then definitely there would be some vibrations of the gold foil, there would be some movement of the gold. But here we are assuming, just for the sake of our calculation, that the gold nucleus is absolutely stationary. In reality, it will suffer some recoil, as in case of all collisions. But as a proton is approaching, it will experience the electrostatic force and it will get deflected along this path. Question is, what is the change in momentum? We are given the kinetic energy of the proton, incoming proton is T, and this distance as D. We are given the charge of proton is E, and the atomic number of gold nucleus is Z. It is given as that only. So, what should be given to us? So, first of all, we have formula. That is for this deflection theta. So this is one of the formulas which I was talking about, which you will learn. So this is like one of a kind formula in which we can directly calculate the deflection of a particle on the basis of its kinetic energy, the impact parameter, that is this distance v, and the charge on the gold nucleus or whatever this particle is. So that formula is some tan theta by 2 is equal to tan theta by 2 is equal to z e square, or you can say z e into q into k divided by 2 impact parameter b, kinetic energy of the incoming particle t. So I will just explain what are the units in this formula, or what are the values in this formula, because it is not actually clearly visible as well. I'll use a different form, different pen. So again repeating, tan theta by 2, where theta is the angle of deflection. This is k. K is your constant in Coulomb's formula. This is Z. Z is the atomic number of the nucleus. E is the charge on the nucleus. Oh, E is the electronic charge. Q is the charge of incoming particle, that is Q. And D is the impact parameter, and T is the kinetic energy. So this is the formula which we have. Right. So from this, we can find what is the change in momentum of this proton as it flies by the nucleus. A pretty interesting thing, right? So again, we are considering classical mechanics here. We are not considering what you say modern electromagnetic theory, where if a charge as it is going in some non-uniform field, it is accelerating. So it should lose its energy in EM based form. That we are not considering. We are simply saying that this is classical mechanics and this is Coulomb field. So whatever energy it will have initially, it will also have finally as well. Its final energy will remain T on it. So let's begin. So now, basically, we only have to consider how the proton is moving. As the proton is moving, its kinetic energy is some T. and we'll say it is deflected by some angle theta, like this. So finally, its momentum vector would be like this, right? We can write like that. This is the final momentum vector. This is the initial momentum vector, Pi. So initially it is going along some horizontal axis and it has deflected finally. The purpose of writing this is to understand what is the change in momentum. Change in momentum, delta P, is simply final momentum minus initial momentum. If you were to write final momentum, it is simply P cos theta I cap, because this is I cap direction x axis, plus P sin theta j cap, and subtracting from it the initial momentum of the incoming particle. So the incoming particle's initial momentum is P only. It will be P I cap. So as you can see, the momentum of the particle initially and finally is same, right? Why? Because energy has remained same. We'll say whatever Coulomb energy the particle acquired in coming close to the nucleus, it will be returned back to the particle when it has reached infinity. So that means electrostatic potential energy is returned to the particle, so its kinetic energy remains same. Since kinetic energy remains same, its velocity remains same. Velocity remains same or speed remains same means its momentum also, magnitude of momentum remains same. So that's why we have put the magnitude of momentum as P here, here, and here. We can calculate the magnitude of change in momentum, delta P. It is P cos theta minus 1 plus P sin. If we calculate the magnitude of this whole thing, it would be, it would come out to be, after calculation, if we calculate all of this, it would be some P outside. It would be cos theta minus 1 whole square, right? Plus sin theta whole square and square root. So you know which formula we are using? We are using a square plus b square and its square root. If I have vector ai cap plus bj cap, its magnitude is a square plus b square and square root of that. Now when we are opening this, cos theta minus 1 whole square plus sin theta whole square, it will become cos square theta plus 1 minus 2 cos theta plus sin square theta. So sin square theta plus cos square theta is 1 only. So that means 1, and there was one more 1 which comes from this square, it will become 2. So it will be 2 minus 2 cos theta. Taking 2 outside, it would simply remain 1 minus cos theta. 1 minus cos theta we can write as 2 squared theta by 2. So it would be 2 squared theta by 2 into the 2 which we have taken outside already. Taking its square root, it would look like this: 2 into 2 sine square theta by 2 t and square root of this whole thing. So this is the magnitude of change in momentum for the proton as it is going like this. It could have been easily an alpha particle as well. So this value, delta p, 2 comes outside, is sine theta by 2. So this is the net change in momentum of the proton. Now we have to put the value of P and this angle theta. The kinetic energy of the incoming photon is T. So the momentum is 2mt and its square root. That we can put here. What about sine theta by 2? So we know tan theta by 2, that is the deflection. is equal to KZE into E divided by 2BT. So sine theta by 2, what would it be? Sine theta by 2 would be KZE square divided by the square root of KZE square plus 2B3 square. So we put KZE square in the denominator. So this sine theta by 2 becomes, I'll just write this again. So if we take KZE square in the denominator, this sine theta by 2 will become 1 upon square root of 1 plus 2bt upon KZE square whole square. So this is what sine theta by 2 is. If you put value of sine theta by 2 in the magnitude of change in momentum, that is 2p sine theta by 2. So it would be, instead of p, we have to write root 2mt. So it would be square root of 2mt divided by 1 plus 2bt upon kze square whole square. Yes. So this is our final desired value. So thank you for joining. Have a good day.